Let me welcome you to this lecture. We have now discussed about three different classes of organometallic compounds. That is, we have discussed about the chemistry of pi acceptor ligands, and then we also talked about pi donor ligands as well as sigma donor ligands, and finally we also discussed about main group organometallic compounds. So now we will begin our discussion on homogeneous and heterogeneous catalysis, and to begin with we will discuss about a very important class of reactions observed in organometallic complexes or organometallic compounds. So these class of reaction is known as oxidative adhesion, and there is a related reaction which is known as reductive elimination. So we may have already discussed about these type of reaction, that is oxidative addition as well as reductive elimination in earlier lectures, but here we will discuss these reactions in more detail. So the oxidative addition reaction, it's a reaction where a coordinatively unsaturated metal complex undergoes addition of ligand, and this is accompanied by the oxidation of the metal center by 2 units as well as increase in the coordination number by 2 units. So we can give one example of oxidative addition reaction, that is the reaction of viscous complex with molecular hydrogen. So we can write this reaction to illustrate the oxidative addition reaction. So that is viscous complex, iridium complex, where the iridium is in +1 oxidation state, we can see. Now, once we do reaction with molecular hydrogen, what is going to happen is that hydrogen, the dihydrogen molecule, so what happens is that hydrogen hydride ligand essentially come and attach to the iridium center, and meanwhile the coordination number of the complex or of the metal center increases to 6, and the addition takes place, of course, in a cis fashion. So an octahedral complex is resulted. So this is what we obtain, and what we see is that apart from the increase in the coordination number here from from 4 to 6, the oxidation state of the metal center, that is iridium, has also increased to +3. So apart from addition of 2 anionic ligands, that is the hydrido ligand here, the oxidation state of the metal center has increased, and this type of reaction where we add anionic ligands to the metal center, and this is accompanied by increase in the oxidation state by 2 units from, in this case, +1 to +3 oxidation state, and also there is increase in the coordination number from of 2 units. This kind of reactions we call as oxidative addition reaction, and this reaction we can write a generic way as well. That is LNM complex undergoes oxidative addition reaction with a molecule XY here, and when the XY bond is going to get disrupted during the reaction, and both X and Y are going to coordinate to the metal center in the resulting product. So LNM X as well as Y, this is the new complex that is formed, and meanwhile if this is N plus M was in N plus oxidation state before the reaction, this is going to become N plus 2 plus oxidation state is going to be oxidation state for the metal center after the oxidative addition reaction. So we can note down what happens during the oxidative reaction. That is oxidation state of the metal center increase by plus 2 units. Then at the same time, coordination number of the metal center increase by plus 3 units. And also 2 anionic ligands are added to the metal. So all these reactions, in case of oxidative reaction, these states are essentially states essentially happen. Now let us look at some of the examples of oxidative addition reaction, because this reaction is part of many catalytic important catalytic cycles. We have already seen how viscous complex undergo oxidative addition reaction with molecular hydrogen, as well as in case of hydrogenation of olefin by Wilkinson catalyst. Also, the oxidative addition is a part of catalytic cycle. So we can write the so that is the Wilkinson. This is PPH3 catalyst undergoes oxidative addition reaction with again molecular hydrogen during the hydrogenation of olefin. So again, what we see, rhodium is in plus 1 oxidation state here, while in the product, the oxidation state of rhodium has increased to plus 3, as well as the coordination number has increased to 6 from 4 over here. Then another important reaction where oxidative addition happen during the catalytic cycle is during the conversion of methanol to acetic acid by the Cativa process. So in this case, an iridium complex square planar iridium complex, where again the oxidation state of iridium is plus 1 because the complex is monoanionic here. It undergoes oxidative addition reaction with methyl iodide during the catalytic cycle, and this gives us again the complex is monoanionic, and if we look at the oxidation state, because now we have 3 anionic ligands, methyl, and 4 anionic ligands. So the oxidation state of the iridium metal here is again class 3, and we have oxidative addition of methyl iodide taking place during this reaction. So another important example of oxidative addition reaction that we can look at is during the palladium catalyzed Suzuki Miura cross coupling reaction. Of aryl boronic acid with aryl bromide. So during this reaction, the palladium catalyst, that is the active catalyst, is this, undergoes oxidative addition reaction with aryl bromide, and this gives us a 4-coordinate palladium complex, while in this case the oxidation state of palladium was equal to 0. We see here in this case the oxidation state of palladium is class 2. So oxidative addition of aryl bromide has taken place on this catalytically active species. So these are some examples of oxidative addition reaction. Now if we look at these reactions, what we see that is that for oxidative addition reaction to take place, certain conditions must be fulfilled, or otherwise the reaction cannot take place. That is, we have seen that in all cases the coordination number of the metal center increases by 2 units. So the first condition that must be met for oxidative addition reaction to take place is that the complex, the precursor complex, must have back-end coordination sites. Or coordination unsaturation must be present. So all the complexes that we have seen where oxidative addition took place were either 4-coordinate complexes or 2-coordinate complexes, and because back-end coordination sites are present in these coordination geometries, that is why oxidative addition reaction can take place only in such low-coordinate geometries, not in high-coordinate geometries like octahedral complexes do not tend to undergo oxidative addition reaction. The second important point is that the metal, which is choose a metal which has the two oxidation states, two stable oxidation states separated by 2 units, that is now apart from this condition, there should be one more condition that should be fulfilled here is that the higher oxidation state should be energetically accessible, and then only oxidation reaction can take place, and as well as it should be stable enough so that the formation of the complex in higher oxidation state. Then the third condition here is that metal must have non-bonding electrons. So because what happens is that during the oxidative addition reaction, two new metal to ligand bonds are formed. So the metal essentially should have some non-bonding electrons left, or otherwise it won't be able to form new metal ligand bonds during the oxidative addition reaction, and that is why the presence of non-bonding electrons on the metal center is again another important criteria that must be fulfilled for oxidative addition reaction to take place. And the final condition is regarding availability of suitable orbitals. Now what we see is that so if we can give one example, that is FeCO4 2 negative say. This is a 4 coordinate complex, but this is an 18 electron complex. Even though this complex is 4 coordinate complex and it has coordination and saturation in it, this complex will not be able to undergo oxidative addition reaction simply because of non-availability of suitable bonding orbitals. Because what we see here is that in order to undergo oxidative addition reaction, this complex will have to undergo use non-bonding molecular orbitals, and filling electrons in these non-bonding electrons will essentially destabilize the parent complex itself, and that is why such reactions do not take place, or oxidative addition reaction do not take place in essentially 18 valence electron species because of non-availability of bonding molecular orbital or non-bonding molecular orbitals. Because in this case, in case of 18 valence electron, we have learned earlier that all molecular orbitals which are bonding in nature or non-bonding in nature are essentially completely occupied, and only anti-bonding molecular orbitals are left empty in case of 18 valence electron species, and that is why 18 valence electron species do not tend to undergo oxidative addition reaction, and instead only 16 valence electrons or 14 valence electrons, 16 valence valence electron species or 14 valent electron species only undergo oxidative addition reaction because of the availability of the suitable molecular orbitals for this purpose. So what essentially this sums up these criteria is that the complex which has to undergo oxidative addition reaction should also be electron rich. So only electron rich metal complexes can undergo oxidative addition reaction, and that is the reason why what we see is that only late transition metals, not the early transition metals, undergo oxidative addition reactions, or the complexes of late transition metals only undergo oxidative addition reaction because these complexes are electron rich complexes. Now let us talk about the mechanism of oxidative addition reaction. Now the mechanism of this oxidative addition reaction essentially is dependent or is controlled by the nature of the XY unit, that is the unit on to where the sigma bond disrupts and the two parts essentially get attached to the metal center or the complex as new ligands. So when we write ln m plus n plus xy ln m n plus 2 here and x as well as y, right? So the sigma bond between x and y essentially gets disrupted or ruptured, and x and y individually as anionic ligands get attached to the metal complex over here. That is the oxidative addition reaction, and the nature of xy essentially decides the mechanism or the pathway through which oxidative addition reaction are going to take place. Now when xy is a non-polar molecule, like H2 or O2, this sort of non-polar molecules, and what is going to happen is that the reaction, the oxidative addition reaction is going to proceed through a concerted process. This oxidative addition concerted pathway, that is the xy unit keeps coming closer to the metal center, and the metal to x and metal to y bonds keeps forming, while the x and y, the bond between x and y continuously gets weakened essentially. So not the first, the disruption of the disruption of the bond does not take place initially. Both these bond formation and bond breaking processes take place continuously and in a concerted pathway. That is what we mean by this mechanism. So we can take this viscous complex once again. Addition of viscous hydrogen to the viscous complex. So what happens in here is that because hydrogen or dihydrogen is a non-polar molecule, sorry, we will write the transition state here. So this sort of tree-centered transition state is essentially, it leads to during the concerted reaction pathway, and eventually the HH bond here gets disrupted and these two iridium hydride bonds are going to be completely formed, so that we end up with the product here. So this is how the reaction proceeds when we have a non-polar molecule via the concerted pathway. We can also see that this complex also undergoes oxidative addition reaction with molecular oxygen in a similar way. And in that case, again here, what we can write here is this is going to be the transition state, because oxygen, there are two, the bond order for the oxygen-oxygen bond order here is 2. So one of the bond remains intact between the oxygen and oxygen here in the product, and we end up with this sort of a product when we do oxidative addition reaction of Husker's complex with dioxazine in this way. So then the reaction pathway is different when we use polar molecules. When XY is a polar molecule, say for example, we have seen one case already where we used methyl iodide as the substrate here. So methyl iodide is a polar molecule, and the reaction pathway in this case is going to be different as compared to what we see in case of non-polar molecules. So here in this case, it can proceed via SN2 electron transfer mechanism. So that is, we can have say ln m plus CH3I essentially gives us this sort of species. And then this will eventually lead to the formation of in this way. So that is what we have seen is that the reaction proceeds now in an by using a SN2 mechanism and 2 electron transfer process. It's a, and that is the case when we use polar molecules like methyl iodide during the oxidative addition reaction. Because the reaction can also take place via a radical pathway. And in this case, the mechanism involves essentially one electron transfer. It is ln m, and we have CH3I. We can have ln m I. Let's say again a radical and CH3I. Another radical and CH3 radical over here, and this gives us ln m CH3. Again the same product. You can write over here. Only the mechanism now involves radical one electron transfer process. So this is how the reaction can take place when we have polar molecules like methyl iodide. What we have seen is that transition metal complexes can disrupt the bond between two hydrogen atoms in dihydrogen, and this essentially gives us oxidative addition reaction take place, and we end up with this sort of dihydride two complexes. So hydrogen bond can be disrupted by transition metal complexes. That is what we wanted to say. Now, similar reactions are possible for CH fragments as well as CC fragments. So these fragments can also undergo, this CH bond can rupture, and the units that we obtain may undergo oxidative addition reaction here with the metal complex, as well as CC fragments can also, the CC bond may break down, and the units that are formed may undergo oxidative addition reaction. And we have examples of this sort of reaction. One very beautiful example is where CH bonds get ruptured during this oxidative addition reaction, and the units that are formed essentially bind to the metal center thereafter. So this reaction takes place in an iridium triphenyl phosphine lead complex. So when we heat it up at 165 degrees Celsius for a longer period of time, what happens is that one of the hydrogen atom, that is on the ortho carbon atom on this phenyl ring of this triphenyl phosphine, essentially has strong interaction with the metal center over here. And this kind of interaction of a CH bond with a transition metal center here, this is a covalent interaction, not hydrogen bonding interaction. We should be very specific about this. That the hydrogen atom here is covalently attached to a carbon atom, as well as it is covalently attached to a transition metal center at the same time, and such interaction we call them as agostic interaction. We have already mentioned about agostic interaction in one of the earlier lectures. So these are agostic interaction, and this hydrogen atom on the ortho carbon atom of this aromatic ring in triphenyl phosphine essentially has agostic interaction with the iridium center in this way. So what we end up is, after the reaction, this sort of a product is essentially formed, and what we have seen is that this CH fragment here, or the CH bond, got ruptured, and the units that we obtain essentially an aryl ligand over here and the hydrido ligand, they are added to the iridium metal center over here, and meanwhile the oxidation state of iridium increased from +1 here to +3, and the coordination number also increased from 4 to 6. So oxidative addition reaction has essentially taken place, and this reaction is known as cyclometallation reaction, or one also term it as orthometallation reaction, because it is the ortho carbon which is attached to the metal center at the after the reaction is over. So that is why it is called orthometallation reaction, or it is also, we can term it as a cyclometallation reaction. So these reactions are important because not only phenyl CH bond, but also CH bonds from alkanes, unreactive alkanes like methane, can also participate in oxidative addition reaction when the metal center is essentially suitably electron rich, and that is why these reactions are important in CH activation process, because this activation of unreactive alkanes can be achieved by this CH activation reactions involving oxidative addition essentially. So Let us now discuss about another type of reaction, that is the reductive elimination. Now, the reductive elimination is the exact opposite of oxidative addition. So, reductive elimination oxidative addition. So, let us see one example of reductive elimination here. Diazenyl phosphonol ethane, that is the ligand here. If we take this octahedral complex, oxidation state of platinum here is +4, and it undergoes the reductive elimination reaction to give us the square planar complex as well as a byproduct. That is, two of the ligands here, cis ligands, essentially form a sigma bond between them to give us a byproduct here in this way. And the metal complex, what happened here is that the oxidation state of platinum became +2. So oxidation state decreased by 2 units, as well as the coordination number decreased by 2 units. And this reaction, that is why we have seen, is that it's the exact opposite of oxidative addition, and we term this reaction as reductive elimination. So the condition that must be met for reductive elimination to occur is that the metal should be in higher oxidation state. Only then it will be possible to decrease the oxidation state by 2 units, so that we end up with a stable lower oxidation state, and then only the reductive elimination reaction can take place. Secondly, for reductive elimination reaction to take place, we must have bulky ligands on the complex, and that will push the reaction forward, so that ligands are eliminated from the metal complex because of steric bulk. So and the third condition that must be met is that this byproduct, this form, should be stable. So these are the three conditions that must be met during the reductive elimination reaction. Now, the reductive elimination reaction is again a very important step, and this is generally the final step in many catalytic cycles. So we will see some of the reactions where reductive elimination occurs at the final stage of the reaction, catalytic reaction, that is. And the first example that we would like to see is the hydroformylation reaction. That is, we have rhodium, during the reductive elimination reaction, these two anionic ligands are going to form sigma bond between them, and we will obtain the formilated product here, and meanwhile the complex decreases the coordination number, and the oxidation state of the complex also decreases by 2 units, and R CH2 CH2 CHO is going to be formed here after formation of sigma bond between these two anionic ligands here, and we see rhodium oxidation state here is, we started with +4 here, and this is here is, sorry, +3 here, and here it is +1. So reductive elimination reaction has essentially taken place here. And another example that we see is in Sonogasera coupling reaction. So during this reaction, this species that we obtain after oxidative addition, essentially during the reaction, undergoes reductive elimination now to give us this as a product during the Sonogasera coupling reaction. So what we see is that the reductive elimination reaction is a very important step, and this generally takes place at the end of the catalytic cycle. So this brings us to the end of this lecture. What we have learned during this lecture about two important classes, important type of reaction that happens in organometallic complexes show extensively and are part of many different catalytic cycles, that is oxidative addition reaction and reductive elimination reaction. We have also discussed about the conditions that must be met for so that these two types of reactions can occur, and at the same time we also looked at the mechanism of this oxidative addition reaction. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.